Good afternoon, or morning, or evening, or whenever you are joining us from whatever time zone you are in, and welcome to another episode of GEOSTRATA Extra. My name is Brad Keeler. I'm the director of the Geo-Institute, and we are thrilled to have you with us today. Before we get started, we have a quick message to read. ASCE continues to stand with the people of Ukraine as they endure this attack on their freedom and democracy. It is our hope that peace can be reestablished and to avoid any additional casualties. ASCE and GI have members in Ukraine. We, of course, wish them and their fellow citizens safety and peace during this time. So welcome to GeoStrata Extra. I believe this is the first episode, because of some weird scheduling quirks, of our third season. We are really happy to be back, and an in-depth interview from the February-March issue will be ensuing today with Ed Cording about his piece on tunnel boring machines. Interviewee today will be GeoStrata editor Jeff Dunn, and we are very happy today to have a sponsor for this event. It is the Tensar Corporation, and we have a quick message to play from Tensar. Thanks again to Tensar for their generous sponsorship of this session today. And at this time, I'd like to turn it over to GeoStrata editor Jeff Dunn.
Thank you, Brad. And I'll add my welcome to the current edition or issue of GeoStrata Extra. I guess it's not an issue since it's not a hard copy magazine. But today I have the pleasure and will be speaking with Dr. Edward Cording, whose commentary, which we refer to as I See It, titled Filling the Gaps with Pressurized Tunnel Boring Machines, was published in the current February-March 2022 issue that had the overall theme of tunneling into the future, and really covered that theme and topic in a number of very interesting articles and commentaries. As Brad mentioned, my name's Jeff Dunn, and I'll be the interviewer today for this GeoStrata session. A little background on myself. I'm a senior principal and single practitioner consultant with my own firm in Walnut Creek, California, which is near San Francisco. I've been an editor of GeoStrata since 2004, so I guess in only a couple of years it'll be my 20th anniversary assisting on this fabulous magazine. Our speaker today, Edward J. Cording, has contributed to the geotechnical engineering profession for more than 50 years. He's recognized as a world-renowned authority for improvements in theories and investigation of rock stability for slopes and underground excavations, a variety of types, and for developing an efficient means of calculating, measuring, monitoring, and analyzing ground movements due to tunneling and excavation, with particular attention to safety in unfavorable environments. He is a professor emeritus from the University of Illinois at Urbana-Champaign, where he served in the civil and environmental engineering faculty for over 35 years. And his interest in the impacts of underground construction on existing structures in urban areas started with his work on the Washington Metro subway in the 1970s. Quite a groundbreaking project overall. Dr. Cording has received many honors, including election to the National Academy of Engineering in 1987, an ASCE's Martin S. Kapp Award in 1983, the Thomas A. Middlebrooks Award in 1985, and the Harry Schnabel Award in 2007. And then more recently, he was the Terzaghi Lecturer, which was presented in 2020. So we have an excellent speaker, somebody who knows tunneling and underground excavation inside and out, certainly. As for myself, talking about tunneling and underground, I was thinking about it and I realized I kind of got interested in tunnels back when I was just a child, when I was reading books and started hearing about some of the very, very early tunnels under the Thames River or in Paris or in New York. And I've had a kind of a fascination with it throughout my life. As a geotechnical engineer, I've been able to work on a few tunnel and underground projects. I'm far from an authority on it, and it wasn't the main part of my career, but I've always enjoyed those. Even better, I've been able to visit a number of the tunnels and subway stations underground during construction. And I was thinking back to my first visit to one of those and realized just as after I entered the tunnel in my appropriate safety gear, rubber boots and everything, I managed to slip and fall on a wet spot, falling right on my butt, and fortunately not injuring myself or anything in the tunnel, but eliciting some well-placed comments from a locomotive driver who saw the whole thing about engineers and how they don't belong underground. So it was kind of an auspicious start to my first visit underground in a recent tunnel. This was in the LA Metro Red Line. And after that, I didn't fall again. I got to walk up to the heading where they were excavating with a pressure TBM, sit in the operator's seat, and all kinds of good things to see it. Along with the other visits I've done, I noted in reading this GeoStrata issue, it showed me how the fields evolve and continues to progress, adapting electronic sensors and control to what is a very rough, generally underground construction environment. And that takes us to our topic of discussion with Ed Cording today about how we can better utilize these capabilities to reduce deformations around the tunnel and particularly at the ground surface. Now, during the interview, if you have any questions for Ed, please type them into the comments or chat section of the video feed while you watch. And as time allows, we'll do our best to address those questions as well during our interview today. So with that introduction, Ed, welcome to GeoStrata Extra. Looking forward to talking to you further. Start off with a little background question. I noted in looking through your CV that your bachelor's degree was in geology, which isn't an unusual thing for geotechnical engineering practitioners. But what led you to change from that field to civil engineering in your graduate studies and to your teaching and consulting career in tunneling and underground construction?
Well, Jeff, first of all, it's a pleasure to be with you all and to have you working with me and asking these questions, which are giving me different perspectives on the work that I've been doing. So I really appreciate this opportunity to be with you and at least virtually with other of our colleagues in geotechnical engineering. I was always interested in building. I built 3 forts, and I also built some forts down a little bit underground out in the prairie that when I lived in Illinois, grew up in Illinois. And I went to Wheaton College, which is a liberal arts school, and they didn't have engineering. And I think from the start, I was always interested in engineering, but I discovered geology, and I discovered their field camp in the Black Hills, and we're out mapping the formations. And to me, it was just eye-opening that geology was more than just looking at minerals in a mineral case, pretty minerals in a case. It really was that all that structure was fascinating to me. And then as I went through my geology work, I found a GSA volume called the Berkey volume, and it's still an interesting, relevant volume. And in that volume, it was there were articles on mechanism of landslides by Terzaghi, the USBR, talking about the underground geotechnical problems rather related to dams, the Corps of Engineers. And it just was eye-opening to me that geology really could be part, and a very major part, of our underground heavy construction projects. And so Berkey worked on the New York City aqueducts, and I had a chance to kind of follow remotely or at a distance in his footsteps, working on projects in New York City with the aqueducts or the water tunnels and the subway and heavy rail tunnels into New York City. And so, but I was trying to figure out where I could go, and I was working for the Illinois State Geological Survey, and I was looking at different schools around the country, mining schools and all, and they said, well, have you ever heard of Ralph Peck and Don Deere at Illinois? And I lived in Illinois. I kind of wanted to get out of the flatland, but I got in contact with Don Deere, and he set me up with a graduate program that included more geology, advanced courses in geology, getting all the basics in civil engineering, and continuing on in CE. And then he was taking us out into the field. We're at Logging Corps and looking at projects like the Tehachapi tunnels, just getting really immersed in geotechnical engineering, particularly on the rock end that Deere was involved in. And then Peck was there at Illinois, and his case histories were like, it was like you were there doing the work, and it was like kind of like a puzzle, like putting together a puzzle with too many pieces and not enough as well. But you had to make it, you had to figure it out, make it work, and then and it was like a detective story, and I really wanted to do that. And so that was really how I got started in working with people that were practitioners and teachers, educators. That was, to me, just a wonderful opportunity to get started in working on underground projects. Peck had done the Chicago subway with Terzaghi. We just learned a tremendous amount from that.
Oh, good. It's interesting. Whenever I talk to somebody how they got in the field, that the small things that happen, the people you talk to or that you have a class from that really influence you.
And there are people that, you don't realize how much you are affecting people when you interact with young people that are, the things that you contribute and may ultimately affect their education and practice. It's just, it's really a pleasure to be able to be involved with students, and hopefully we can pass on some of the sorts of things that we benefited from.
Yeah. Well, good. Well, now turning to some more discussion about your commentary. In that piece, you indicated that pressure-faced tunnel boring machines, or TBMs, were first introduced about 50 years ago. So, long time. And for at least the last several decades, the availability of electronic monitoring has been available that's further enhanced the capabilities to control ground movements, particularly in what you referred to as gap number 1 around the tunnel shield, a physical gap. But there's still a need to better coordinate design, monitoring, and tunneling operations. So even though we've had those capabilities, the TBM, pressure-faced TBMs for almost a half century and for several decades monitoring, what is it, do you think, that's prevented that from happening sooner and being adopted more or less universally?
Well, Jeff, it is changing, and to me, it's almost like a revolution. There's been a tremendous amount of change because of these capabilities that we have, and it's the sort of thing that I just wanted to just briefly comment. working on projects for the last 50 years, we were working with situations where you couldn't control the ground in the face of the tunnel. And that wasn't that long ago. It was within the last 20 years that the LA Metro, for example, has adopted the tunnel, the pressurized earth pressure balanced tunnel boring machine. Have been adopted by contractors and a requirement by Metro. And so some of the development has to do with our seams and gaps. Again, saying gaps, but the gaps, seams between disciplines, and that's where I think that we just have to continue to bridge those gaps by people within different parts of these disciplines interested in tunneling, and we need to be coordinating very closely with the various groups that are doing this work. And to me, I think geotechnical engineers are really well placed. The type of background and education that we should be taking the lead in this, in filling these gaps, and we should, we focus on observing the ground behavior and being out there and looking at the geology and looking at the rock and the soil, and looking at those impacts, and those observations are just crucial to our projects, and we're observing more and more through electronic information. But that's really, to me, something that I think we can be doing much more of as geotechnical engineers. Just noting that this gap is not just between designers and contractors; it's also it has been within a contracting organization. For example, the history of tunneling is that the people in the heading of that tunnel are the people, the supervisors and miners in that heading are the people that are at risk. And you don't tell them what to do unless they agree, because it's their risk. They're taking the risk of the safety and all in the tunnel. And that was the approach that was used. And so designers didn't get involved with that initial support or what they had to do in the tunnel. They said, well, this is what I want as a final lining in the tunnel. And, going into a heading, I've observed, for example, when we had a tunnel wheel that was going around, it wasn't, it was a wheel excavator, but it wasn't pressurized. And so if you turn that wheel too fast or turn it without pushing forward, you'll meter material into the heading, and you're going to be losing ground. You'll cause large volumes that can move to the surface and could cause a sinkhole. And so I was in the heading on one project, and I tried to hit the different shifts. And one of the shift, one of the operators on one of the shifts was, let me click here just a second to make sure I get back to the full page here. Sorry. Okay, one of the operators on the shifts was moving the TBM or the cutter head of the shield. It was a tunnel boring machine, but it wasn't pressurized. And he'd move it forward very easily, slowly, and just keep the torque and the push balanced, and trying not to meter in too much material. And so he was doing pretty well. On the other shift, the operator would push hard on the thrust to hold the face, and then he would get torque bound. And I'm standing in the tunnel, and the instrumentation I have is that push ram that's going forward, a hydraulic ram, and you mark it with some muck or dirt, and then just pull your watch out and say how fast is it moving forward. So I'm watching that push ram, and I've marked it, and I note that the push ram is not moving forward, but the head is rotating, and so he's losing ground. And so I told him, I said, you know, you just caused us a night's worth of work to have to fill the void that you just created. And so that's the sort of thing that very much it's under the control of the operator, and it was under the control of the operator in the heading. And what we're seeing more and more, and what I think you'll see in some of the other articles in the February-March issue, is that there is more automation and more guidance for the operators, and more automation that allows them to be able to make adjustments that are within the range of what is needed and can do the control. So that's one of the gaps that we have, and it is being filled. And so I think that there really has been a lot of progress. I'm not sure that we are that we're behind on being able to make the changes. I think of so many things that have happened that we are able to do now that we hadn't in the past. But let's go forward just a couple of slides, and if you could pull up that next slide, Jeff.
Yeah.
Because I think it will kind of point out what some of the issues are currently that we're dealing with, and some of the progress that I think is being made and needs to be recognized and used on our projects. So this is a pressure face TBM, and you'll see this in the next couple of slides, that the next couple of slides on this pressure face TBM, that the chamber in the front is filled with muck, and that's an enclosed chamber. It's conditioned with a foam, it may be bentonite, and that's what's holding the face and balancing the face. And the control on that is the screw. In the next slide, it shows the screw, and that's for the earth pressure balance, and that's what's removing the muck, and it has to be coordinated with the advance so that you provide the required pressure. And so that's what we have done with the pressure face TBM, and that's what's been developed maybe as much as 50 years ago. There's a tremendous change in the understanding. You would not probably have been using that, and we were not using those machines in the United States back 50 or 40 years ago. And it's taken some more development for them to be really reliable and all. And so but the first criterion is prevent that inflow in the face. We don't have to dewater, we balance the water pressure, and as you see on the next slide here, we balance what's in the front of the face with the pressure we apply. And so that's the primary thing that we talk about with pressure face TBMs. And then as you can see on the next couple of slides here, we're talking about the pressurized TBM. And the first thing that does happen, as you can see in the next bit, is that there's the muck that can push out around the cutter head and fill the gap, which is a gap that you have to be able to steer it and push the shield forward, which is going to be on the order of about 20 or 30 millimeters. And so that gap is going to, it can be filled with that muck that comes around, but it's not always consistent. And so what we're looking for on tunneling, and particularly, for example, working in LA, is we want to be consistent 24/7 through the whole project. We don't want to say, well, we're going to be doing it most of the time and then miss. And so this is what's causing the settlement, is the lack of would be the lack of filling in that overcut. And that can cause a couple of inches of settlement. And so the overcut shield gap, now what we're using on our projects and requiring on Los Angeles Metro and required on the large diameter tunnel in Seattle, is that we fill that overcut gap and pressurize it with a bentonite slurry for consistent control all the time. We don't want to lose ground, and that's what's being done. In the tail, as you can see on this last little bit, the tail of that TBM is the grout is injected through the tail, and it fills the gap during advance, and that's become very much a standard, and it has basically eliminated issues with ground loss back at the tail, which can cause 4 or 5 inches of displacement if it's not filled. And so those are things that I think we need to have more progress and effort on using that shield gap and understanding the cause. As you can see in our next slide, there's several things that in practice, we recognize that pressurized TBMs, pressure face TBMs reduce ground loss, and that the muck can fill the gap, but not always. And there tends to be a reliance on estimating what can happen by some percentage of ground loss of the volume of the surface settlement trough that's based on previous projects. And often the source of the ground loss is not well determined. For example, if you're measuring the surface settlement, how much is occurring into the face or on the shield? And typically people will say, well, we've lost ground because the face wasn't supported. And what we're finding is, in projects we've had even, over the last, even after the last 40 years, is that we get the movements, that the movements around the shield are what cause the regular settlement trough for the most part. And so that's the area you really want to focus on in addition to the face in terms of controlling ground. Now, let's go on a bit here to the next slide.
Let's see here. There we go.
There.
My
okay.
mouse wasn't cooperating.
Now go the other direction.
Oops. I'm sorry. Yeah, I pushed the wrong key.
Well, we'll get it, Jeff. Here we go. Okay. Now now we have all this instrumentation that people are doing on projects, but the instrumentation we're interested on for this TBM is not so much what's happening on the buildings. We want to monitor on the buildings just to know that nothing's happening. But what we want to know around the TBM is exactly what's happening around the TBM that is close to the TBM. It's related to how we're operating the TBM. This is the information that I really want to see our projects putting together. And so one of the issues sometimes is that we have instrumentation people doing the instrumentation and the operations doing the looking at the pressures and the operation, but the two often aren't coordinated perhaps as well as they should be. And so with this, now we can identify the source of the ground movements and see what the magnitude is and show that those movements are small and within our criteria such that we have confidence that we can tunnel forward and be under control when we go under critical structures. We're using the borehole extensometer, piezometers in that overcut, and their relationship to the pressure gauges are such that you can tell if you have an outward hydraulic gradient that's holding the ground up, just comparing that shield pressure and the piezometers. And then we now are using HDD more and more in LA. We've got a lot of projects now, several projects that current projects in which we have been using the HDDs as magnetometers to locate oil well casings. But we're also using that right above the TBM, putting an inclinometer in them, and we can monitor continuously. We can install these, extend them under buildings, and monitor right under the buildings that are of concern. So these are the things, that figure shows the things that we need to be concerned with, and we need to be correlating those measurements with the pressures that are being measured on the TBM. Okay. So to me, it's the reason we haven't made more progress. I think we have made a lot of progress, but part of it has been to recognize just where are the causes of the movement, and then try to work between the various groups that are involved, such that we coordinate that effort between instrumentation and for example, and the TBM. And the other item is that the large diameter tunnels, and when you're tunneling at shallow depth, that's where perhaps the most progress has been made in this coordination. And it really started, a lot of it was done in Porto, Portugal, 8-meter machine, and then Barcelona, 12-meter machine, which where they were starting to really pressurize or fill and pressurize that gap. And so we followed up with that on other projects in Toronto, and the Alaskan Way project in Seattle. It was also a requirement, and we're requiring this in LA.
Good. So that gives us some, oh, sorry, Ed.
No, you go ahead.
Okay, so that gives us some really good background on kind of the evolution of from pressure face to pressurized and so on. And you just mentioned Alaskan Way and that view of the TBM, which to me is just really impressive, 57.5 feet in diameter. And you discussed Alaskan Way viaduct replacement constructed with that large TBM, but resulting in surface settlements that were very, very small, which is just an incredible accomplishment to my mind. Are there other aspects of that project you'd like to highlight?
Yeah, in fact, you bringing this question up has caused me to think back to a couple of major aspects that we don't focus on as much with ground control, and then a couple of other aspects with respect to ground control. And that previous slide, by the way, was that that TBM as it came out of the exit shaft, and a couple of people down there. If you look at that upper diagram, you see those little green dots there, green and white dots. Those are people. I mean, that looking at that thing, you're sitting on top of a 5-story building here and looking down at that face, and that was what was being controlled, that TBM, that face, as well as the shield. So going on to this next slide, there's a couple of points that I wanted to make that I think are in addition just to the fact that we had small displacements. If all we were looking at here, Jeff, was small displacements on this, we could add this to the list of projects where this is how much displacement we had on this project. But the question is, why did we have that, and can we count on those conditions? What do we need to do to be able to duplicate that on other projects? What is it that is causing the movements? But the two things that I wanted to focus on was first of all, once that TBM left Safe Haven 3 and went under downtown Seattle in the viaduct and Pioneer Square and the high rises, it was underneath buildings almost all the time. And what I saw with the operation, with the joint venture, Seattle Tunnel Partners, joint venture of Dragados and Tudor Perini. What I saw on that project was consistent operation all the way through, and it's in two major areas that I was seeing this. And one was the area where I'm concerned with, the settlement, but the other area was with respect to the TBM. The life of the TBM and the wear and particularly the performance of the main bearing. This project started out with some major issues during the startup prior to going out of Safe Haven 3. and that there was a 2-year delay in order to put down a shaft, drive the TBM into the shaft, pull the main bearing out, which was about a 2,200, well, with the main bearing and the cutter head on it, was like a 2,200 metric ton lift. So you have to bring in a heavy lift outfit far beyond what a couple hundred tons that you would normally be operating with on a project like this. And so that took a year to make the shaft, a deep shaft, well, relatively deep shaft, but we were still at shallow depth. We had about 50 feet of tunnel above us, but 40 or 50 feet of ground above us, but the shaft had to be 120 feet deep, near the limit of what you would like to do with a big thick, large diameter sequence. And so then a year to replace that main bearing. They brought in a new main bearing, replaced it, replaced all the seals, put it back in the ground, and started up. And so the thing that I observed as they went out of Safe Haven 3 was their control, not just of the ground, but the control of the main bearing and the operation of TBM. More of a mechanical engineering issues. But for example, the temperatures never went above 40 degrees centigrade. That Celsius. That was the maximum value that they would allow, and they kept that. They operated the machine, so they kept that pressure down. They put in a much relatively fluid mix in the cutter head to make it easier to thrust and rotate the head at smaller torques and not overload that cutter head. They kept the pressures on the seals. They have a series of 4 or 5 seals around the main bearing at each location where they have it greased, and they're measuring the temperatures and pressures in those seals. And they make sure those pressures are above the groundwater pressures. So that was all an area that wasn't my work as such, but I saw that was what the contractor was doing, and his performance was just outstanding. Then the other thing that I'd like to kind of point out here, this is a 11 months, 5-day project here that could go through the thing. But it was like when you get in a project that's really working and you see a tunnel opera project, it's all a linear system. Everything has to work. It's like there's a rhythm to it. You can see that the people that are working on it are doing a good job, that they like their work and it's efficient, and that's what I was seeing on this project. So going on to the next slide here, just a couple of points here that perhaps we can cover, but the consistent control, not just, I've talked about the issues with the main bearing, but the consistent control of the face. It's not just that we had small settlement. These were the things that were allowing us to have the small settlements, caused only small settlement. Maintaining the face pressures. The upper face pressure is your guide, and maintaining that even between shoves. They would inject large volumes of bentonite in the chamber to keep that pressure up all the time between the pushes of the machine, which are about 2 meters at a time, and then you'd have an hour or so for erecting segments. And so and you'd have a couple of days on the weekend. So that's when they kept that pressure up, and so they never let it down. They always vented the upper chamber so that any from the muck and the foam, any accumulation of gas bubbles that would cause a large bubble on the top were prevented, so that you didn't get free flow of soil into that upper chamber. They vented that thing throughout the entire drive. Vent that back onto the conveyor belt, but make sure that you don't have a gap up there, a void that's just it's compressed, but it's not supporting the effective weight of the soil. Continuously fill with bentonite and balance those pressures. In granular soils, the top of that machine is like a big plate, and that plate is under pressure, and that is holding the ground up so that gap around that shield doesn't get filled. And so you might, in granular soils, put a polymer in to give it more cohesion to hold the granular soils better and provide that gradient outward that will support the ground. Okay. Going on, just a couple things that we learned. The next slide does show it's not just that we had small surface settlement. We're measuring the settlement a few feet above the TBM, and there you can see that that the settlements were almost zero when we were down at shallow depth. But this is right above the TBM, but got up to about 6 or 8 tenths of an inch in the central part. And the reason was because we were putting a pressure on that machine, which was balancing that flat groundwater level, and basically you had a much higher differential with the overburden. And so the settlement was not due to anything falling into the gaps. It was due to the pressure differential, which is just like an elastic equation. The pressure differential is basically overburden minus the internal pressure. And if you want to reduce that further, increase the internal pressure and you further reduce settlement. But that's what it's due to. And it's very clear from all this instrumentation that was what happened there. So those were the additional things that I wanted to focus on, Jeff, is in addition to just that the surface was small, a tenth of an inch, and it was a little bit larger when we're down at 200 feet than it was when we're down at 100 feet. And so that was due to this difference here. And the opposite of what you'd expect when people say we're going to have large settlement, you expect it to be at shallow depth. Okay, let's go on to the next slide. So there wasn't any ground loss, and the displacements were elastic. This is the machine after it came out of the ground. Next slide.
And we're on. Okay, so you mentioned in your commentary, Ed, that obviously you've just talked in good detail about the control that was put in place and maintained. But there were also, in your commentary, you talk about some of the planned mitigation measures, some of which were implemented, I think some micropiles, as I recall, that caused more surface settlement than the tunneling efforts themselves, and some of the other things that were contingencies, such as compensation grouting, that, if needed, might cause some displacements as well, but fortunately wasn't used. It kind of made me wonder, overall, was there wasted mitigation on the project that could have been avoided, in hindsight, of course. So,
well, and I don't want to answer this in hindsight, of course, because it wasn't, we weren't operating here as Monday morning quarterbacks. When I say we, I'm talking about the project. I was able to work with them, and I had a tremendous opportunity, but there was the history of this thing, and somebody should go in and really summarize all the different things that people were thinking about to do for this, to driving the world's largest tunnel boring machine under downtown Seattle, with foundations that were within 15 feet of the crown of the tunnel. And I told some of the people, I didn't get involved with the design of it. I told people, I said, I'd like to wait and work with the contractor on this. And I really wasn't invited anyway, but I was able to work with the proposers on this, one of the proposers, and then finally with the other proposer who actually got the job. And the thing that is interesting is all the different things that people were thinking about as to what is it that we can do to mitigate this. I told some of the designers, I said, this is really a major, you've made a tremendous decision here. Instead of not only the decision to go underground and not just replace the viaduct with another viaduct, which the community, the waterfront community in particular, was totally against. Very much against, and they convinced WashDOT that we needed a tunnel. And then you say, okay, well, why not just run 2 tunnels? Well, they're large tunnels. They wanted to run them up different streets. And so they said, we're going to do 1 single tunnel. And I said, you really made a bold decision here. And I'm not sure if I'd been working on it, how I would have looked at it and working with you on that part of it. But what I did see was they really made a tremendous effort to mitigate in different ways. And so some of this was what you're seeing here, Jeff, that they did. But even working with the proposers, one proposer, just as they were thinking through the problem, somebody in the proposal group said, well, we ought to put in $50 million in order to take care of settlements that exceed an inch that we're responsible for at that point. On the high rises. And I said, I don't see how you're going to figure out that you're going to need $50 million for repairing high rises. I said, it's not going to help you in getting a bid. And so there's just a lot of different concerns that were being raised and all. And so when the contractor got the project, and perhaps you could go forward, I think, perhaps to the next slide.
Okay.
Just for a moment. He had this test section at the south end. He basically proposed that they extend the test section so he'd have a larger distance in order to do the testing. He put in secant piles between the viaduct and the tunnel to make sure that there weren't any movements that could occur against that. So those were some things that he did. He had all sorts of ground improvement plans in there so he could drive the TBM into it and check things out. He was able to cut back on a lot of that once he got started. But those were all things a part of what the contractor was thinking about. And then, and let's go back to the previous slide then again, Jeff. And so here, what was happening was that those micropiles were placed between the foundations and the piles and the tunnel, kind of angled between to kind of provide a fence that would reduce settlement. And so that was something that that we saw them do that seemed to be that it perhaps in hindsight, or if it had been put in later, but they might not have done. So that was really the only thing that I saw under that section. But we saw that our movements were small, and we proposed. I say we again. The joint venture proposed to Washington DOT that they eliminate that. They agreed because of they saw what we were doing, and so those were some things that did get changed. As you go on to the next couple of slides here, let's flip on one more. And here we are starting underneath the viaduct. And we're going under the viaduct on a weekend and with no adverse effects. First time that I think that the project was above the crease on the Seattle Times with a positive statements. And at this point on, the project really was just receiving some really good credit for what it was being done. That's a pressurized cylinder we have that is supporting the ground. Going on to the next slide. Tunneling underneath, we're tunneling here underneath Pioneer Square, and there's this one building we're going by, and at that location was where the compaction grouting was supposed to be installed, and we didn't. The building was in very poor condition. It was an old brick bearing wall building, and you could see on the foundation that different piles in different periods had been installed. And you could see settlements and displacements in the foundation and the basement that were on the order in excess of a foot. And so they went in and stabilized that foundation with grade beams. You just don't want to be going by, even with no movement, you don't want to be going by a building that's sort of metastable. And so they did do that, but they left out the compaction grouting. And so on the next slide, you can see us moving the tunnel project, moving into in front of that building on the left. And the settlement right above the TBM was closely monitored. It was about 1 millimeter. And the surface settlement, we couldn't pick anything else up. And so it really proved out what we said and what WashDOT approved was we didn't need the compensation grouting.
Okay, so good introduction to Alaskan Way. So in not just introduction, but discussion, I should say. So in your commentary, you talked about filling the physical gap, and then you referred to gap number 2, which you said was an indication of that there was a definite need for better coordination between pressurized TBM operations and geotechnical monitoring, which you've talked a little bit about. But that coordination is critical to reducing the settlements. And for both the Alaskan Way project and another project in part of the current project on the Los Angeles metro system, this coordination seems to have occurred and to have been very successful, as noted in your commentary. How was this brought about?
Okay, let's go forward to that next slide. I think it describes some of what was being done. And you could kind of click through these a bit to fill the page out. But we start out with the Seattle Tunnel, Washington DOT. WashDOT said they put a lot in there in addition to things like requiring the micropiles and requiring the compensation grouting and all. They really, this is the part that really was the mitigation as far as I'm concerned. It was things that related to the TBM itself. The Construction Monitoring Task Force had to meet daily. It was a meeting between the Seattle Tunnel Partners and Washington DOT Construction Management and Engineering, and then you got down to the tunneling level, and you have the TBM operation, and you have all that instrumentation that comes out. There's about 5,000 tags on those machines, a tag being the measurement of something that's being recorded with time. And so that's coming out with that instrumentation. And then there's all the data that's coming into to the project from the instrumentation team, but that's being coordinated and worked through with that geotechnical monitoring team that's working directly for the joint venture, employed by the joint venture and within the joint venture. And they are the ones that are assembling that information and coordinating it with the TBM operation. So to me, that's the key to bringing that all together, and then working then with senior people each day that operations and geotechnical is providing that information on a daily basis to the construction monitoring task force. On the next slide, you'll see a little more about that, Jeff. So the Washington DOT, excuse me, the WashDOT required a very detailed description in their specs of the construction monitoring task force. They required that the bentonite be injected to fill the overcut gap. And then they required borehole extensometers on the closest spacing I've ever seen of averaging 50 feet over the whole TBM drive, something like 150 extensometers. And Bill Hansmar, some of you may know, Bill's worked on projects with PB at that time and worked on LA Metro, and he basically, I told Bill, I said, Bill, you just really overdid it. You put these things on 50-foot centers, and now I'm working for the contractor and doing that work, who is doing that work. And I said, I will be forever grateful, because the contractor had the resources to get the information that I think it allowed us to show what did happen around that tunnel boring machine. The other part was Seattle Tunnel Partners and working with Tony Sturbies, who was in charge of that geotech team. And I said, you know, over on the Mike DePonio's job in Sound Transit, JD, he put in vibrating wire piezometers. Why don't we do that? So Seattle Tunnel Partners added vibrating wire piezometers and all the extensometers, tremendous amount of information. And then they had that team not only reporting daily, but every time that machine went forward 2 meters, they would put out a report summarizing the information. So that's the sort of information that was coming out and was needed in order to be confident that the world's largest machine going under, you know, all these structures in downtown Seattle we had confidence that it was working. If we go on to the next slide, I wanted to talk a little more about LA Metro. And here I'm working on the other side, you might say, for the tunnel advisory panel, and we basically have an approach with LA Metro, and the management in LA Metro is supporting this fully and implementing it, is that to demonstrate consistent ground control on all projects all the time. And that's really the sort of thing that's in the specifications. They're requiring the filling, they're requiring that they put gauges on the shield, the perimeter of the shield, to measure those pressures. The first time that was required, the manufacturer said, well, why do I have to do that? And well, the short answer was that your client wants it, but the reason was that we want to be able to show that those pressures are being controlled. And it was, what we're finding is that our surface, not just only the surface settlements are less than 0.3 of an inch. We're down right above the tunnel. We're getting on the order of 1/10 to 0.3 of an inch right above the tunnel, depending on the pressure we're applying. But we get that because we're filling the gap. So next slide will show that. Okay, the shield pressure is balancing with the upper face pressure, and it's hard to kind of pick it out, of course, but but the green line is the upper face pressure. And the other two plots are the upper shield pressures around that tunnel shield. Now, if the overcut gap isn't being filled, it will not track with the face pressure. And you'll see much more variation. This is, I mean, I picked out the best one I've ever seen. I mean, the two are just the same, but you can have a case where between the shoves, for example, it's showing that that the pressure might drop off a little bit more on one gauge than the other, but this one is just perfect. But that's what's giving us the confidence that we are filling the overcut gap. You go on to the next slide. We have the chamber pressures in the bottom and the upper part of the TBM. The upper chamber pressure is always lower because of the head gradient, and then the middle, and then the lower at the top, the highest pressure at the top. And those need to be separated in with about 0.8 of a bar difference between upper and lower in order to show that you are, you don't have a big gas air bubble, or that you are, and that you're you're basically balancing with this fluid pressure of the muck. And so that's the sort of information, extremely valuable. That's being put out, and this is being done by the Metro project. Not the contractor in this case is putting this information out. At least this is what I'm seeing. We're seeing up as being in Metro. And it's being summarized by project management team that has a lot of tunnel experience. Next. And this is one of those horizontal inclinometers. It went 700 feet and underneath some critical structures, and it shows it right above the TBM, and you can see from one diagram to the next, that's the advance of the TBM, and that's what's happening, and it's happening over the TBM shield and about a 0.3 of an inch settlement. And we're down now with the pressures they're applying, we're down around 1/10 of an inch, right above the machine. You can't even pick up the surface settlement. And so those are the things, and it's the construction management team, Metro's construction management team, that is really doing a lot of this coordination and working with the contractor. But the contractor's performance here is excellent. Next.
Okay.
I think that's the end of that one.
Yeah. For
question. But you know, both the
where's my mouse?
One has to do with the contractor, Jeff. The contractor meeting requirements that were coming from WashDOT, and here, you know, what I'm seeing is again the owner, LA Metro, is saying we are going to have consistency. We want to be able to show that when we get to the next project, or that when we go in with third parties and we have to go in under somebody else's building, that we can say with confidence that we can do this with these machines.
So, gap number 3 in your article, Ed, you're in your commentary. Anyway. It talked about a better linkage between the building protection study, which is done on any major tunnel these days, of course, and requirements for TBM control and monitoring during construction. Made me wonder, do you think most tunnel designers have a suitable understanding of TBM operations to really bring this about, or is that lead to a disconnect there, kind of inherent?
Yeah, and I started thinking about it as to what is the tunnel designer, who is it, and how do we deal with this, and what I think that is this, I guess you could put the question in another form, is it that he doesn't have suitable understanding, or that he doesn't have knowledge of and confidence in what in the methods that will be used to control the TBM to achieve this ground control, to achieve these small settlements. I mean, he's doing this early in the project, and he may not have the information that says the TBM will be operated in this way. This will be required on the project. And so I think that's a big part of it. And typically, you know, when you talk about tunnel designers, you can start talking about really a range of different backgrounds here. And you have tunnel designers that I've seen tunnel designers on projects, even in design build, where they get involved with designing the lining, and they're dealing with the alignment, and they may deal with ground modification or compensation grout schemes, but they don't want to be involved with the contractor's means and methods. And then there are other designers in projects or engineers on other projects that have more of an interaction with that part of it. So that's one of the issues there, of course, is to be bringing that together. And I think that what we want to do, and I think on LA Metro, what we're trying to do is we want to have in place, we have in the Metro design criteria requirements that for the TBM operation that can be relied upon by the people providing these reports. Now, typically these reports, ground building protection reports, are prepared often by geotechnical engineers, and they will look at the mitigations of compaction grouting, compensation grouting, jet grouting, and permeation grouting, and that's after they have calculated the settlements based on an assumed ground loss. And they get that from the literature because perhaps they don't have the information. It says the TBMs here are going to control to a factor that's much different than what you're picking out of just some general information from machines that you don't know the actual history of how they control the ground. And so I think that you want to have that in place such that the team that is often geotechs that are doing this building protection study can rely on that and say that TBM will be operated in this way. And not only as we're saying that in the spec, but we are going to have on this project where there's going to be monitoring, and there will be a startup section where they're going to monitor and ensure before the machine advances that it is under control. There will be hold points before you get to critical structures. So something that gives the designer on this side the confidence that this will be done. And so I think that to me is the major part of this. And I think that it is a situation, I think, where you just don't want to be giving this to a firm that is maybe involved with some design, but really isn't close to the TBM the means and methods. And it may be that you need to have joint efforts on this. But that should be part of that should be what is being laid out on the project by the owner and by his consultants to make sure that happens.
So it sounds like design build contracts are really more amenable to this sort of thing. They sort of put that coordination in place contractually, I think so. Well, moving on, that we expanded on your commentary, but given your many years and wealth of knowledge and enormous experience in tunneling, I wanted to ask you a few more kind of generalized questions, as it were. And I know we're
sounds like you're trying to set me up, Jeff.
Well, I'm looking at the clock too, so
yeah, I know, and I know we've got a few minutes here, but I would like to comment on some of your comments here. That we've got a few 10 minutes maybe or 5. Well, we need to have some discussion too, so perhaps yeah, that's fine. But you just go ahead on how you want to handle it, Jeff.
Yeah, if we have time, we can loop back to that comment. So,
but I do think it's that. The design build, most of the projects I'm on are design build. It's not necessarily that they are, there's a coordination, there can be a coordination problem there between their joint venture construction and the designer, the instrumentation, and that's a major area that we're concerned with as well. So, there's no contracting method that's perfect, but that's one of the things that needs to be worked on there as well.
Okay. Well, going on to a more kind of general question about your experience and career, What's the most baffling problem you've ever encountered on a tunneling project, and how'd you tackle it?
You know, that's a good question, you know, Jeff, and I've got a case history on that I'd love to tell you sometime, but we don't have time for it. And the other part is that I looked up, I hadn't heard us use this term baffled on our projects and all, and I looked up the definition of baffled, and again, I think it's a very useful term, but interesting term, but the dictionary says it's feeling confused, totally bewildered, or perplexed. And it kind of reminded me of, what was that song? I thought it might have been was it South Pacific, where it was a love song, you know, and it was something bothered and bewildered am I? And so to me, baffled is maybe, this brings up some important concepts, but baffled is not the way I see it. It's essentially, we've got to design and build in this environment of uncertainty. We're never going to have all the answers, and we have to build, and that civil engineers have to build in such a way that their project works despite the fact they don't have all the answers. And then, but the other part of this is the observations, and we have to make the observations. And Jeff, I'm not sure we have time to go through this, but I found working for working on projects where was building damage, and working sometimes with insurance companies that were had a claim against, where there was a claim against the insurance company's contractor who had done a nearby excavation. And so this happened on what is called the Monroe White House. It was right after the War of 1812. And Monroe inherited a White House that had been burned down by the British, and so he's basically living on Pennsylvania Avenue, I think it is, in this 4-story, beautiful early 1800 townhouse, and so the conservators of that townhouse now have found damage in the townhouse. And let's go on, take a look at it. Particularly look at the left side of that building. These gorgeous arches and fan lights inside, and a stairway that goes up the left side. The next slide shows what they were seeing. And the cracks that were occurring above these archways and all on the left side of the structure in the stairwells, or on each floor between the stairs. And one of the things that red shows, you know, a white crack shows up pretty well on the red. And so they brought in a conservator, and they had some geotechnical, perhaps, I don't know, consultants that said, we think it's water coming from the nearby excavation. It's come under here, and it's kind of like the underground river type concept that has undermined our foundations. And so the conservator said, well, we got to take down all of this and rebuild the stairs. You know, it's priceless stuff, I think. A couple hundred years old, and they're going to tear it all down. And so I was asked to take a look at it for the people that had been doing that excavation. They said, we couldn't have caused this. We're 100 feet away. How could we have caused this damage? And so I started looking at it. The next slide will show a little more. And here on the left side is this new building that's now in place, but that was where that new building had an excavation, and they were underpinning the west or left wall of that 11-story building and hotel, and what was happening is that it was tilting due to that, and it got 3 millimeters of settlement between the two buildings, and the characteristic of that brick bearing wall building that is basically the Monroe White House was that it's just brick walls with timber setting in the wall. There's no tie between the walls. And so, the characteristic of the building on the left, which is a 1920s building, was all concrete floors tied into brick. And so the concrete floors are giving it some lateral connection. So if you get a displacement on the left side, that's going to, the building is side swaying, and it's side swaying a very small amount. And the left wall or the west wall of that White House, the Monroe house, is essentially right up against the other bearing wall of the hotel, and it's going to go with the hotel, because that stairwell in that left side is a weakness. So the next slide shows what's happening here, and the interesting thing about this is that that 50 millimeters of settlement was just due to the fact that they used green timber 200 years ago, and the intermediate timber bearing wall was settling. And so that's what you see there, but then you could pick up a few cracks here and there, and that 3 millimeters was giving you that small distortion. So the thing that's interesting here is these are targets of opportunity, often poorly monitored and instrumented. The building is the instrument, and that's what the observations that I think were so important. The observational method, not the observational method, but observing what the conditions are and using that building as an instrument, essentially, to tell you what had happened. So, the next slide, I think that covers that case history.
That covers that one, yeah.
But to me, it was kind of the other end of what we've been dealing with here, Jeff, is that, we're talking about not causing any damage, and where I've seen damage and been able to get information that we've used in our research and numerical analyses and model testing for building damage is based on these targets of opportunity.
Okay.
This is not something that LA Metro would be doing or WashDOT would be doing.
Yeah. Well, I think from that, talking about that issue, that wasn't a baffling problem, like you said. So I find that sometimes the words that we use commonly, if you go to the dictionary, you find out you're really
well. To me, it was a fascinating question. It really caused me to start thinking. It wasn't so much that people may have been baffled, but that's, as engineers, we shouldn't be baffled. We should be trying to figure out how we do it, what to do.
Yeah. Well, a couple more questions, and then we'll be finished up for the session. But one thing that you have a background, your bachelor's degree was in geology. You talked about how you started out in that field and things you really, really enjoyed about it. Geological education, which at one time was very, very common, I know for myself, for civil and geotechnical engineers, has been kind of waning. It's no longer a requirement in a lot of universities. And it's just at a time when tunneling, which is very often, particularly in rock, but in soils too, is dependent on geologic conditions, obviously. And it's a solution that may be available and very useful for many of the nation's urban transportation and infrastructure problems. Do you think that's a problem for today's tunneling practitioners? And is there any solution? I mean, the easy thing I thought of is, okay, make them all take geology again.
Well, maybe you've answered it in part. But, you came out of Berkeley and Tor Brecka was there and several others, that were kind of close to that and bringing that in. I don't know. I mean, we've got good faculty there now, of course, but I think that we saw that in Illinois. Don Deere was proud of the fact that he was a professor of civil engineering and of geology. In other words, it wasn't a combined department. It was two appointments. And so when we came to Illinois, we were taking geology and engineering geology and geology courses, as well as civil engineering. And I think it's extremely important, and that's been an effort. For example, talked to some of our people in Illinois and saying, they're saying we want to make sure they still continue to take those courses, even though we may not have an engineering, do not have an engineering geology program in the geology department. We want them to be taking geology. So I'm not sure what the answer is, but I think it's, it's important. I mean, we've got AEG and Geo-Institute and GSA and the ARMA, and to me, I'm an engineering geologist and I'm a geotechnical engineer, and I think I find it just extremely valuable. I haven't been close to it in the academic side to say what is going on there, Jeff, but I think it's something that we ought to be paying more attention to, because to me, it's really at the heart of how you approach geotechnical problems, is having that geologic background. That's the ground, that's the material we are working with.
Yeah. Well, I'd have to agree with you on that. So one last question, Ed. What do you think is your most lasting contribution to underground engineering and construction practice? You've been practicing for 50 years now, and that could take you a while to ponder, but I imagine you've got some kind of
yeah, I've got a couple of slides. I just pulled up 3 slides that cover these areas, at some of the areas that I think have been important. And I could make the short answer is that I'm not sure that hopefully a lasting contribution would be one that I won't be around to be able to say what it is. But one of the things here is I worked with Marco Boscardin on in his research at Illinois, and we basically came up with this relationship between what happens in the building, the angular distortion, the ground movements, what happens with ground movements and excavations and tunnels, and then the impact on buildings in terms of the angular distortion and lateral strain. You sum those, and that really gives you, for buildings, it gives you the principal extension strain. And that turned out to be the boundaries between these values. But I think that this slide just points out that the focus I've had in the research, going from, first of all, we started looking at what happens right around an advancing tunnel. And then we looked at the distribution. And then we started looking at, well, what's happening to the building and the damage in the building. And so that's been kind of an important area, and this is being used widely in the industry, and I think it's a very useful diagram. And the thing about it is that when we start talking about the pressurized TBMs, sometimes people say, well, we only have to have slight damage. It'd be just some cosmetic, which is mostly what that is, cracks in the plaster. And we're saying, and what we're doing now in the LA Metro is that we're holding settlements down so that we're down in the bottom of that negligible range. We don't want to be going in and dealing with third parties that have to redecorate a series of houses, or they have to redecorate a series of houses along our alignment. And I think you don't, as we progress in our capabilities as engineers and contractors to build and control the ground, I think we find that the communities are also advancing in their demands, and maybe rightfully, but the demands for not being interfered with and not having to deal with impacts. And so it's important, and that's where we're going to be on these diagrams. And that's what I was describing for the pressurized TBM. Now let's go to the next one, which is another area that I've worked on a lot. And this lecture, this article we've had in GeoStrata, isn't covering the rock side of it. But to me, this was the pilot tunnel to at DuPont Circle, and they had done some borings, and the borings just didn't give them the picture of what this is. When you go back and look at the borings, you can pick it out. And you look at the RQD, something that Don Deere established back when I and I was able to work on some of that early work back when he did this in the 60s. But the RQD tells you, is a good indicator here. I found that on Metro, if the RQD was less than 50%, we probably had one of these, what we call shear zones, several feet of fractured rock with clay gouge and that sort of stuff. And so that kind of was one way of tying it together. But to me, the orientation of these features, angling right down along the pilot tunnel and along the station, and you're trying to support something that's going to slide in on you or fall off on you, and running parallel to the tunnel is a major issue. And so to me, what I find in looking at the rock is that we're trying to understand geology and behavior. How is it going to behave? The first thing is to get the geology right, not just to get some sort of classification scheme that says this is class such and such, and that we need such and such support. That's kind of rule of thumb stuff. What we want to understand is, what is the geology? And then what is the behavior? And if we understand geology and behavior, we can figure out how to design these things. And then finally, the third part was, and that's what I felt throughout all the work we've done in rock, and particularly, the East Coast metamorphics from Atlanta to Philadelphia to Washington to New York. We're dealing with these metamorphics, and this is some of the worst of it, right there in the middle of Washington, D.C. But we really want to be, as geotechnical engineers, we want to be good observers of these things, and that's something we bring to the table on projects, to be out there and looking at it and figuring it out. We don't want to just focus on classifications or codes. We want to see what it is it, and how is it going to behave. If we can do that, we can understand how to build it. So, a lot more to talk about there, but and then this was what the displacements were. And the thing about it is that those displacements were extremely significant on the sidewalls. We were getting displacements in on unsupported sidewalls, and because the joints were so planar, that we were getting the movement also occurring up above the top of the tunnel, and that can only occur if the rock isn't dilating, if it's not interlocking. And so that was a very unique characteristic, and we did the post-construction numerical analyses, the discrete element, distinct element that really were interesting studies that Lee in this case did to compare what Mahar was measuring when he was Jim Mahar out in the field on the Washington Metro. So look at the ground, look at the orientation, understand the geology, and then figure it out. Finally, just getting back to the last topic, the first topic really we talked about, is that one of the things that stopped the use of the large diameter TBM for stations is that people are saying, well, it needs to be down here at the depth that I'm showing, and that's causing access shafts to be deeper, access outlet by escalators to be more difficult. And what we're seeing now is, with the type of control we have, we're looking at designs and projects where we can we don't have to use a diameter and a half of cover above a 40 or 50 foot tunnel. We can, or even larger, we can go in with diameters that are more on the range of 3/4 to 1 diameter and control the ground very well. That puts us down at depths that are on the order of 40 feet. And that's the depths that we can work with these types of projects. So this is one of the applications that's going to be seen more and more. In San Jose, they're planning it. They've talked about it in other projects. And we're going to see these large diameter TBMs where we are really reducing the use of excavation in the street. And the cost of a station brace excavation is extremely high, and there's a lot to be achieved by being able to put the platform and even a mezzanine in the tunnel. So that's some of the results of what we've been talking about for the last hour. So those are kind of the three areas that I would say are things that I've been working on and contributing to.
Okay. Well, wow. We've covered a lot of ground and supported a lot of ground, I guess.
That's a good analogy.
Yeah. Some phenomenal details about Alaska Way that I'd heard all about the bearing replacement and the access shaft and everything, but hadn't heard all of these details about it, and knew the tunnel was built very, very successfully. And I think you've brought that home. I want to thank you and thank for your commentary and for your time here and questions. And is there anything you want to add in closing real quickly? Or
I don't have anything else to say that I think of at the moment, but I've just enjoyed being able to talk with you, and it just I thought your questions just really they really caused me to think beyond just presenting something and think about what is it that we've been doing, and we are in a wonderful. I can't think of a profession that I'd rather be in. I mean, the people I've worked with, the engineers, the contractors, the owners, people that are committed. I mean, on these projects, no matter how tough it is. I mean, when that TBM went down in Seattle, I was having dinner over at one of my favorite restaurants, and they said, "Oh, we're so sorry to hear about the TBM, with the main bearing, for 2 years. We're so sorry to hear about it." And I said, we've got a great team of people. There are a great team of people on the project, and they like to be on projects where they don't have to deal with things like that, but they know how to do this, and they will make it happen. And that's what happens in the tunneling industry, is that designers and contractors are committed. You can't do 99% of the tunnel and say, well, I'll just deduct 1% for that last bit because it's too hard. You have to finish the job. And so it's a wonderful industry to be in. And the people I started working with 50 years ago that were graduate students and young engineers, the thing that I didn't expect is to be still working with them 50 years later, and they're making tremendous contributions. So it's a great industry to be in, and I do appreciate GeoStrata's focus on this, and your questions have just made this a very special event for me.
Oh, good. Thank you, Ed. And I'm glad you liked the questions. I enjoyed thinking them up and asking them and hearing your responses. So, Brad, did we have any other things we can cover? I know we've gone a little long time-wise, but
just to wrap up, well, first I'll say I'm partial to the Washington Metro stuff because, certainly some unique projects, some of the deepest tunnels in transit in North America, maybe the deepest. So very cool. And I really liked that presentation, Ed and Jeff. A great job as always with the questions. So everybody out there who's watching, if you liked what you saw today, and like I always say, you probably did because you're here at the end, click subscribe, click get notifications. We'll let you know every time we post something to the channel. Thanks everybody for being with us today. Look for the next episode of GeoStrata Extra popping up on our Eventbrite page soon. Our next live stream will be a week from today, and it will be the second installment in our student research series. You can sign up for that on the Eventbrite page as well, and we hope you do so and that we see you in the chat for that event. So Jeff and Ed, thanks again. This was a great session. Everybody learned a lot, I think, and a lot of fun. And I think, Ed, everybody was looking forward to seeing you. So thanks again, and we will see everybody next time.